Okay.
So our speaker today is Dr. Antoine Doury from the French National Centre for Meteorological Research. Antoine is a member of the Large Scale and Climate Modelling Department, and his research focuses on regional climate modelling using machine learning techniques, which is what Antoine's going to be talking to us about today. So, Antoine.
Yeah, thank you. During the presentation, I will talk about mostly my PhD work, which I finished like 2 years ago. And the aim of my PhD was to develop these tools like the regional climate models emulators. And I will present a bit why we do that, and one reason is that we want to explore, we need it to explore extreme events evolutions under climate change. And today I still work at CNRM, and I'm a permanent researcher there. So first, one kind of really recent, famous, and tragic extreme event was the Valencia 2024 extreme flood. So what happened there? I'm sure everybody heard about it, but what happened there was that very strong precipitation in really short time, and it is due to like the cells which were giving precipitation were blocked by the mountains which are just behind Valencia, and so it stayed blocked there for hours, and then so many runs in the mountain range just behind. I'm not an expert, but just quickly, which made that there was this huge flood, plus the modification of the land use and the river trajectory, which probably played a strong role in the catastrophic event. And the question is that we need to adjust the probability of such events in the future. So we need to have high resolution enough climate models and climate projections to simulate correctly the orography and the precipitation cells and so on. We need to have a precise tool enough to describe all the conditions well enough that we can address the question of of the probability of such events. And as you know, it's an extreme event, so really rare, and we need to sample a maximum to identify really, to have a good estimation of the distribution. So that's why that's why we will need RCM emulators. But first I will go back on some definitions. I'm not sure everybody here is familiar with climate models. So what is a climate model? It's a numerical representation of the climate system. So we put the physical equations of mass conservation and fluid mechanics in some numerical tools. And the aim is to simulate each of the components of the climate system, so the atmosphere, hydrosphere, cryosphere, land surface, and biosphere, to simulate each of them and the interaction between all of them. And this under some forcings that can be natural forcings like the sun or volcanoes, for example, or anthropogenic forcings like greenhouse gases emissions. And this is what we will do. Like we have this tool which is a representation of the climate, and we put some input about the CO2 emissions, for example, or CO2 concentration in the atmosphere, and we see how it evolves, how the climate reacts under this forcing. So we have sorry. So how does it work? We have a gridded representation of the planet, 3D, and we perform simulation. So the simulation is the time evolution of various variables that are used to describe the state of the system at a given moment. And we put different forcing and see how the climate react. What we have to know is that there are really expensive tools, and the more complex, the better we describe all these components and their interaction, the more expensive they are. So we have to make some trade-off between the complexity, so how well each component is described, the length of the simulation we want to do, the resolution, which is like the size of the grid box we use to cover the planet, or the number of simulations. As you can imagine, there are many sources of uncertainty when we do climate simulation, and the three main ones are like the uncertainty about the future of our societies. So we draw some socio-economic scenarios and which are represented by what we call RCP forcing. We will see that later. So we have some like 3 or 4 or 5 trajectories about how the society could evolve, and we associate to it greenhouse gas emission. Then there is the model uncertainty. Like, as I said before, everything is not perfectly represented. So we have some kind of error on the model, on one given model. And then there is a last source of uncertainty, which is the internal variability. We know that the climate system is chaotic. This is the butterfly effect story. And so it can take one trajectory or one other. And which make that at some point extreme event will happen. So here we have a representation of the share. If we watch the picture on the figure on the right, of the share of each source of uncertainty across time. So in green, it's the uncertainty associated to the future of human society, and we can see that at the beginning we know kind of the trajectory we are taking, we know the emissions we are taking, and the more far we go, the more uncertainty there is. And this is at the global scale. So here the choice we will make is the biggest uncertainty. And at the beginning, we can see that in orange, the internal variability plays as a strong, as a bigger share, and then it decreases because the other are taking more space, and then because the scenario is taking more space. And then there is the uncertainty associated to the models, which stays quite big all along the time. So we need to make large ensembles of simulation to take into account all of those uncertainties. So we make various scenarios. We need to use many models to have not the same errors each time. And then we need to make several simulations with each models in order to take into account the internal variability. So we have different kind of climate models. The most common tool is the global climate models. They cover the entire planet. They have generally a resolution between 50 to 250 kilometers. And so here on the right, you have what look like Europe at 150 kilometer resolution. And for example, me, I live here in the south, in south of France, near the Pyrenees. And I know that the Pyrenees are going up to 300 meters, 3,000 meters, sorry. But here they barely reach the 1,000. So we can see that at this scale, 150 kilometer, at this resolution, we do not have a good representation enough of, for example, the Pyrenees, but also the Alps and any mountain range. Also the coastline, we can see that it's not properly defined, and we know that the coastline has a, for example, what happened in Valencia, it has strong impact on the meteorological event. But because of their resolution, they have the advantage to be cheap enough to make many and long simulations. So we can assess some of the uncertainty. So there are the right tool to study the climate from the global to subcontinental scale, but we cannot assess the local extremes event and their impacts. So we need to downscale those simulations because it's not possible to have something at high resolution over the whole planet. So we have another kind of models, which are the regional climate models. And we talk about dynamical downscaling because we have a tool which is really similar as the global climate model. It's the same representation, it's climate model with the same representation of the physical equations. But this time it will work, for example, only on Europe. So we have a RCM here at 12 kilometers, and we can see that we have a much better representation of the mountain range and the coastline. But it will work only on this domain. So it receives at the border of the domain information from a given GCM simulation. We say that the GCM simulation is driving the RCM. So there are many studies that have proven the added value of RCMs, and what we can see is that actually there is added value even when we go back to the GCM resolution. So for example, we have here on the left a simulation at 12 kilometers, and on the right a simulation at 150 kilometers. No, sorry. The first line is the GCM simulation, the second line the RCM, so low resolution simulation, then the second line the RCM simulation, and down there the observations. And we have the on the left the simulation interpolated on a 12 kilometer grid, so the one of the RCM, and on the right the simulation interpolated at 150 kilometer. And we can see that at 150 kilometer, the RCM simulation is closer to the observation than the GCM. So when we go back, even so at the scale of the RCM, 12 kilometer, the added value is obvious. But even when we interpolate back to the grid of the GCM, we still conserve added value. So here we can see the importance of having high resolution simulation. But they are still very expensive. It's not because we cut we take only a piece of the planet that we really win. Like for example, when we take the GCM at 150 kilometer resolution, we have about 30,000 points at the surface only. While here in the RCM we have about 200,000. So it's much more expensive to run a RCM at 12 kilometer only on Europe than a GCM at 150 kilometer on the global scale. And because we have a new model in the chain, we have new uncertainties from the model itself, because it's not perfect again, and from the interaction with the driving GCM. We don't really know how the RCM will transform the information from the GCM. I hope I'm not losing anyone here with all this. I know it's a bit complicated, but it's important to understand what I'm doing after. And what we can see here on the right, so it's the same figure as before, looking for temperature and precipitation over winter and summer at the share of the sources of uncertainties. And we can see that, for example, when we look precipitation in winter, that in orange, the internal variability, so the uncertainty associated to the chaotic nature of the climate. When we look at local scales, like at subcontinental region, we can see that this share is much more important. So we need really to have a large amount of long simulation to have a good estimation of what is a future extreme event to properly sample. So to study all these uncertainties, we need to have multiple RCM driven by multiple GCM and with different scenario of emissions. So the yellow is the historical, and then the more the red, the warmer is the scenario. Is that we need, so we have those GCMs, large scale, low resolution, that are too low resolution to give us information at local scales. So we need to downscale them and we use RCMs, which are regional climate model only on a limited area domain. But these ones are still really expensive. And they bring a new source of uncertainty. And so to address this uncertainty, what we need to do is to build large matrices where we have multiple RCMs driven by multiple GCMs driven themselves by multiple scenarios. And for each of these triplets, we need to make several members to study the internal variability. So this is not doable with the RCM we have. They are way too expensive. And it's not getting better because they are getting more and more complex to really well represent the phenomenon that are happening at local scales. Before, what I will talk is 12 kilometer RCMs, and we are moving to kilometer scale RCMs. So it's really way too expensive to imagine fill up this kind of matrices with many simulations, with many members for each of the triplets. There is another way of doing downscaling is empirical statistical downscaling. So the idea is to estimate the relationship between the low and the high resolutions in observed data. There are different strategies. I will not go really deep in the details here. But basically the first one strategy is to learn the physical relationship between the atmosphere and the local surface variable. And I did highlight this one because I will talk mainly about this. And then there are two other strategies, which is to link to make statistical correlation between a low resolution model, so GCM, and some local observations. Or another one is to generate a realistic series of temperature, for example, conditionally to a GCM simulation. So because we want to learn statistical relationship, you can imagine that in the last years, there's been many methodology using neural networks that have appeared. Probably the most famous one is DPSD by Banyomenida in 2020. And there is a review of such methods in which was published this year. But the big problem of this method, the big limitation is that they assume the stationarity of the past-present relationship. Because we learn this relationship in observed data, they are past or present, and we assume that in a much warmer climate, this relationship will hold. And many studies tend to show that it's not the case, or at least not always and not everywhere. So we propose in my PhD a new tool, which are RCM-emulators. And it means that what we want to do is to apply a statistical downscaling framework inside RCM simulation to learn the relationship between the large-scale atmospheric condition and high-resolution variable of interest, but inside the RCM. Why we want to do that? Like that, we don't rely on observation anymore. We can use RCM existing simulation to learn the relationship in the past or in a future climate. We can use different scenarios, and we have much more data to train. And once we have built this tool, we can apply it to GCM ensembles and then explore the different sources of uncertainties. So very quickly, now I will go a bit more in what I did. This is the data I was using. So the RCM we are talking is the one developed at CNRM. It's called Aladdin 63. It doesn't really matter. And it has been used to produce like about 10 simulations. The main one where we will focus on is the one that are driven by this GCM, the CNRM GCM, and we have 4 simulations: the historical, a scenario where we have low emission, a scenario where we have middle emission, and a scenario where we have really high emission until the end of the century. In blue, is my training set. And in green is the closest simulation, which will be my test set. So I will everything, most of the thing I will show you will be evaluated on this simulation, the green one. All the other simulation here on the right. So there are other simulation. So Aladdin driven by other simulation coming from other GCMs. We have each time historical and RCP85, and I will use them quickly to evaluate a bit the transferability of the tools when we move from the world of this GCM to another one. So now I will move a bit on the conception of the emulator. So I worked with two variables, temperature and precipitation. Here I will not, I will explain you quickly, but what is important I work in what I call a perfect model framework, meaning that I always stay in the world of the RCM simulation, meaning that I take my high resolution RCM simulation, okay? I choose my predictors, I will present after, and I upscale them to the GCM grid because this is what I want to learn. I want to learn I make it looking like a low resolution simulation. And then I take my target variable, temperature or precipitation, and I train the emulator like this. And then for the evaluation, what I will show you is that we will stay in this RCM world. Like that, we have an exact comparison to make. This you don't need to keep in mind too much. It's a bit complicated. So what are the inputs? The input, there are a daily description of the atmospheric conditions. So we have various variables, okay, at different level in the altitude. So 2D variables on this given domain here. And you will see that what I want to predict is kind of the same size of the domain. And a little technical point is that, so here we have different variables with different like range of values. Like for example, the geopotential, we are talking about like the values, the range of values is around from 2000 meter to 5000 meter, and here the humidity we have something like 10 at the power minus 10. Okay, so really small values here, really high. So we need to normalize. And the choice I made was to normalize each map by itself, by its own mean and its own variance. So I always have map with mean 0 and variance 1, but doing that I lose some information, which I put back through a 1D vector that I will show you after. Okay, so I have my 2D maps showing like the general atmosphere circulation, and a vector, a 1D vector, which is giving some temporal information, I call. And then we have also the forcings that are coming in this vector. So here is the network I use. I'm sure you're all familiar with that. It's a classical U-Net. So I put all my input here. And then there are two little extensions to the classical U-Net, is that I just talked to you about the 1D input. I make that the U-Net goes down to a 1x1 vector, and then I put the 1D input here. And then when we rebuild, because we have a higher resolution, so higher, bigger maps in output, we need to extend a bit the decoding path of the U-Net. Okay, and the tool is quite efficient because we need 1 to 2 hours to train on the GPU, and the prediction is instantaneous. Okay, and so we chose the U-Net because it's fully convolutional, and because we're working with images, we thought that it was better. And so I told you I worked with two variables, so the temperature and the precipitation. What is interesting to look at here is that the temperature, okay, it's something which is kind of normally distributed, so the mean squared error is at least not too bad for a loss. But when we talk about precipitation, we can see that it's not at all normally distributed. We have a really right skewed distribution with a really heavy tail. And so here I will explain back a bit later, but we chose to work with a loss function that we designed by ourselves. So here it's kind of the mean absolute error plus a coefficient, a term here, which is penalizing the network when the truth value is underestimated by the prediction. This is the max here. And the stronger was the true value. The coefficient here says that the stronger is the true value, the stronger will be the penalization. Okay, so now let's see some result we have, and I will start with temperature. So I just chose a random day. So just to remember, we have this is kind of the low resolution we are looking at. And then on the RCM is the high resolution on the left, and in the middle is what is doing the emulator. So we can see that the emulator is performing quite well. We have a good reproduction of the spatial structure over the island, for example, over the mountain range in Italy, the Pyrenees, even the hotspot here in the south of the Alps. We also have it in the emulator. And this is just for a random day. And we have almost perfect spatial correlation between the two maps. But the other thing we can look at is the temporal correlation, or just the time series. And we can see that, so in blue is the low resolution temperature for a point in the Pyrenees and a point in the Balear. And we can see that the emulator is able to reproduce well the red series, which is the RCM1, almost perfectly. And it transforms the blue one differently in the 2 points. Like we can see here that the seasonal cycle is really modified by the emulator, while here not that much, but the variability, the variance is much better reproduced by is corrected by the emulator. So we are quite happy. We can look at the mean or the 99 quantile, and we have the difference map on the right here. You can see that in both cases, the emulator is doing quite a good job. We have some little bias, but it's like 0.3, less than 0.3 degrees of bias over values that are much bigger. So at the moment, for us, it's fine enough like this. And when we go to 99 quantile, the results are a bit less good with a cold bias, underestimation of the 99 quantile, but this is kind of expected when we work with mean squared error loss. We can see that what is interesting also is that we don't have really a structural bias due to the mountain, the coastline, or we have kind of a general bias on the maps. So now you remember, so this was on the simulation that I told you is my test simulation. And what happened when I move to another simulation where I change a bit, I try to move in a different space of value, because so I test the emulator on these other simulations here. So driven by a different GCM. So I don't change the training set, I just change the evaluation set. We can see that the RCM here is like 2 degrees warmer. It's the same period, but the RCM is 2 degrees warmer than in the previous simulation, and the emulator is able to follow that correctly, even if we have a bit more cold bias than before. Okay, but we can see that we are like 2 degrees warmer in average, and the cold bias is at maximum 0.8. So and the average is 0.2. So we are here again happy. But when we look at the 99 quantile, it's something we can expect, but the lowest, the worst mistakes are a bit bigger. So what happens is that we are now applying the emulator to a simulation which is globally 2 degrees warmer, and we can see that the highest extremes are a bit complicated to reach. So what we tried is to add another simulation to the training set, and we can see that if we watch at the difference map in the 99 quantile, so we add another simulation to the training set. We have now 4 cross here in the training set. We can see that we managed to correct most of the bias. If you look at the difference map here on the right, if I move from before to now, what the result we get is much better. Okay, so here I was just saying that if you move from this one to the one before and come back, that the map on the right down, we managed to correct by adding one simulation to the training set, which is warmer. We enlarge the value of space that the emulator saw, and we managed to recreate. If we can move to the next one, we managed to, the emulator is able to properly do the extreme of a warmer simulation. We can move to next slide. So then the other thing we can look at is the climate change to evaluate the emulator. And here we can see that, for example, on these 2 simulations that have really different warmings, one like the one up and the one down, we can see that the emulator does a great job in both cases. So now we can move to precipitation and on the next slide. So just to remember, the precipitation, they have a really right-skewed loss distribution. So we have a lot of days with no rains, and we have really few days with really high precipitation. But in and these days are playing a lot in the mean. So the mean squared error is not a loss function adapted to this problem. And we designed this loss function, which is the mean absolute error plus a term penalizing the network when it underestimates strong precipitation. And the stronger the precipitation, the stronger the penalization. Can you move to the next slide? So here again, I just illustrate what we are doing, what we are having, and what is. So in green we have the emulator, in red the RCM, and what we were super happy about is that we have something. The emulator is doing a series. So this is time series for 1 year at 3 given points. The emulator is able to produce a precipitation series. And we can see that on these 3 points, we have very different kind of precipitation. Like in the Alps, we have a lot of variability with a lot of strong precipitation. In Paris, we have precipitation also all along the year, but much less strong precipitation. And over Rome, we have really dry spells that the emulator is able to do as well, and as well as really strong precipitation event. Can you move to next slide? And the emulator is able to do it. So when we look now at some given days at the maps, so here again we can compare on the left with the low resolution. We can see that the emulator on the right, on the extreme right, and the RCM in the middle, we can see that the emulator is doing quite a great job. Even if, for example, when we look at the day on the second line, we miss some trajectory, for example. Okay, we can see this line in the middle, which is not well reproduced by the emulator, but we are really happy still with what the emulator is doing. So we can move to next slide. So we can, again, like before, watch evaluate the emulator under climatic aspect. So we can look at the mean on the first line, the percentage of dry days in the second line, or the 99 quantile on the lowest line. And in all cases, we can see that if we look at the column on the right, that the emulator is doing quite a great job with less than 15% bias always. One point that we can highlight is that the emulator is doing, especially over the mean, the first line, the emulator is doing a bit too much precipitation where there is a lot of precipitation, and a bit too low precipitation where there is not a lot of precipitation. And on the next slide, I compare what happened when we take some classical loss. So I don't take this. So the one column is when the loss is the MSE, and the second one is when it's the mean absolute error. When we look at the column of the MSE, we can see that we have quite good results when we look at the mean climate. But whether we look at the percentage of dry days or the 99 quantile, we have strong biases. Okay, the emulator with the MSE loss is doing way too much, like is underestimating a lot the percentage of dry days. So it's doing way too much small precipitation, and it also misses the extreme precipitation. When we look at the mean absolute squared error, we can see that the emulator is then doing really good job when looking at the percentage of dry days. So it's able to do days with less than 1 millimeter precipitation, but it underestimates any other precipitation. So this has been more like deeper analyzed in a paper which was published this year. Can you move to the next slide? So here is some conclusion on the tool. So the idea was to have a tool to produce high resolution climate projection. How we choose to do it is to take a neural network, a UNet, that we train inside RCM simulation in order to apply it to new GCM simulation. And so the aim of the tool was to capture the relationship between low resolution description of the atmospheric circulation and some high resolution variable. And we saw that it works because we have a good reproduction of the spatial structure and the temporal variance at the grid point scale, and a good ability to reproduce extremes. We also have a good understanding of the strengths and the weaknesses of the tools and how to improve. For example, we saw that for temperature, we can adapt the tuning set to correctly explore the space of possible values, and the network is doing better. And for precipitation, with a tricky distribution of precipitation, we can see that the loss function can help to better capture the relationship. So I think I'm going to stop here because it's 1 hour already. I guess you have a lot of plans. There was a little example of application, what we can do with it, but I think I prefer to keep time for questions if there are. Don't know what you think, guys.
Thank you, Antoine. Do we have any questions for Antoine? Yep.
Can you hear me, Antoine?
Yeah.
Yeah. Okay. Good presentation, by the way. Thank you. I was wondering if you had tried at all with overshoot scenarios. Because I imagine those kind of scenarios where the hysteresis of the climate model probably changes the patterns between high resolution and low resolution may confuse the model. Like, have you tried looking at that at all?
No, but I agree. I agree. It's something interesting to look at. I would say that we need overshooting scenarios in the training set as well. One way, yeah, or actually, or maybe we need more input variables to capture somewhere that there was overshooting. But I agree, it's an interesting question, something we need to look at, and we didn't really so much because in the generation of simulation we are using to train and to evaluate, there were no overshooting scenarios. Like one the downscaling of CMIP. Today we are working with the downscaling of CMIP 5. I don't know if you're familiar with that. but so it's the previous generation of GCMs, where they were, and we are not using overshooting scenarios.
Nope. Okay, thank you.
I have a question about the motivation. So you mentioned in the motivation that for extremes you have to run models for a very long time to get the distribution of extremes. In order to train this model to reproduce the extremes well, would you have to run your very expensive RCM simulation for a long time in order to train it? And if so, does that make it more or less useful as a technique for modeling extremes?
So what I said is more that we need to have many simulations of the same with the same GCM driven by the same scenario to have to cover the internal variability. What we hope is that we still manage to reproduce the most extreme event, even with training and on a shorter sample. The aim is that we will downscale. We will downscale a maximum of new GCM simulation with the tool, and we hope that the training set was enough. But yeah, it's always a trade-off, like of how many simulation we do for training or not. So, like, I guess the more simulation we have, or the longer simulation we have, the better it is. But on the other hand, we need to cut at some point. At the moment, we are quite happy with what the tool is doing. Like we already tried to downscale a large ensemble of simulation, and it works quite well.
Okay, do we have any more questions? Doesn't look like it. So we thank our speaker again.
Thank you.